So, a quick introduction. OpenMP has been out since November 2018. OpenMP, as you know, is an open standard, which is portable across vendors and platforms. And it is based on directives, attempting to make programming easier. And at the same time, it supports various types of parallelism. So, with OpenMP Offload, we have one host and one or more accelerators. And we have the target construct, which tells the compiler that we need to transfer control flow from the host to the device. So here we have an example. It is a simple SAXPY computation. We have the pragma-OMP target. We start computation on the host, and we have memory allocated on the host, of course. Now, when we reach the pragma-OMP target, memory is implicitly allocated on the device. When we have the pragma-OMP target map, the data is transferred from the host to the device. The code is executed on the device, and at the end of the computation, the data is transferred back from the device to the host. We're going to discuss these concepts more when we go to the actual code. Here you can see the case study application. This comes from the bioinformatics domain. And it is the Needleman-Wunsch algorithm that is used for protein or nucleotide sequence alignment. It is a dynamic programming algorithm, and we are going to discuss the wavefront pattern that characterizes this kind of algorithms. So on a high level, we're not going to get into too much detail of this. We have like two for loops that go over the two sequences. And for each element of this two-dimensional array that we have here, there are three values that are calculated. And then we pick the maximum of these values, and we assign it as the value of the specific element. Regarding to matching the letters, or like whether it is a amino acid or AT or GC, we have DNA. And yeah, so the way we parallelize this is we block the code into blocks of elements, and we can parallelize in a wavefront pattern. This means that parallelism starts from the top left part, where we execute the first block, and then once we calculate the values of this block, we can then proceed to the next under diagonal, where we have two blocks executing in parallel. Once this is calculated, we go to the next one and to the next one, and this is like the wavefront parallelism pattern that we have here. And then within each block, we have the same kind of pattern that we can exploit. And this kind of pattern is because of what I showed in the previous slide, these kind of dependencies that we have for each element on the top left, and left element. Now we are going to switch to the actual code, and we are going to see. First, we are going to start with taking a look at how the code that we have here corresponds to the algorithm that we just saw on the slide. So I'm going to go to the NW function here, and you can see that we have two big for loop structures. One is this one with nested for loops itself, and another one at the bottom. All right? So, and I have copied, like in ASCII, a similar example to what we saw on the slide. So the first for loop structure that we have here calculates the top and left part of this two-dimensional matrix. Effectively, it calculates what is above the main under diagonal here. So it calculates the block number 1 and the blocks with number 2. And the other for loop, the other big for loop, calculates the main under diagonal, which is the bigger one, marked with 3, and the ones that are below it. Recall what we discussed about the wavefront parallelism pattern. So block marked with number 1 is executed first. And once this finishes execution, the blocks marked with number 2 take their turn and are executed in parallel. So you can see that we have an increasing amount of parallelism as we start from the top left until we reach the main under-diagonal, where we have the maximum amount of parallelism. And then parallelism starts decreasing again until we reach the bottom right block. We have parallelism within an under-diagonal, from what we discussed, but not across. And this can be seen from where we actually put the Pragma OMP parallel for directive, which is the for loop that loops over all the blocks within the same under-diagonal. The next nested for loops loop over the elements within a single block. They loop over the x and y dimension of a single block. They calculate the three equations for match, delete, and insertions that we saw on the slide, and we won't get into detail. They pick the maximum value and assign it to the specific element. All right? So this is basic code with basic OpenMP directives for running on the CPU. So I'm going to source the environment variables from one API, so we can compile and run this, as well as the subsequent GPU offload. So I am going to run make, which is just like the typical flow for compiling. We are using Intel compiler and the -q OpenMP flag for enabling OpenMP on the CPU. And I am going to run a simple example. So the first parameter is the number of elements for each of the two sequences. So we're essentially using two sequences of 16K letters. The number 10 is a penalty value it has to do with the algorithm, but we won't discuss this. And the last parameter is the number of threads. So just running with one thread, two threads, you will see that we are getting some performance benefit. It's not linear speed up, but we do not have abundant parallelism. It is like this wavefront parallelism. And just like to note that whatever we are running today, both on the CPU and what we are going to run on the GPU, is running on this laptop. So we are using the integrated Intel GPU for running the OpenMP offloaded code later. But of course, the same concepts you can apply to the discrete GPUs that are on Intel's roadmap and that are coming in the next few years. So now let's move. So we ran this on the CPU, and now I'm going to move to the offload code. So I have copied the contents of this file exactly as they are into this file, with the only difference that I have commented out the Pragma OMP parallel 4, which is for the CPU, and I have substituted with the explicit way to do offloading. This is the most explicit way. It does not mean that this is the most performant, as we are going to see. So what you should note here is the target keyword, which specifies that the block that follows is going to be offloaded to the offload device. As I mentioned, in our case, this is going to be the integrated Intel GPU. And you are also need to check to see the map clause, which has to do with the data transfers from the host memory space to the device memory space. So here we have two arrays that we are working with in the offloaded code. The first one is called reference, and this is annotated with a to keyword, which means that we are going to transfer the data from the host, that is the CPU, to the device. The input item sets array is going to be used as an input and as an output in our offloaded code. So we annotate it with the keyword to from, which means that we are going to copy this from the host to the device before the start of the execution. And we are going to copy the results of this array from the device to the host at the end of the execution of the offloaded section. So let's go and compile this. I have created a separate make file. So this one uses the Intel compiler again with the appropriate flags. And I am now going to run this same code like I did before. And you are going to notice I will spare you the wait and tell you that this is not going to run anytime soon. So why is that? As I mentioned earlier, the way that we set our OpenMP Offload directive is not ideal. And why is that? It is because we are doing the data transfers every time for every iteration of the outermost loop. Of course, this is not intuitively correct. We are doing redundant work here. So we actually need to do the data transfer once for all the iterations for the parallelized offloaded loop. And this is an important thing to keep in mind always when you do offload programming, that data transfers can be a very big bottleneck. So you always need to make sure that you optimize the way that data transfers take place. So what I'm going to do here is I'm going to take this. I'm going to put outside the outermost for loop, and I'm going to change it to the Pragma OMP target data map construct. So this construct is telling us that whatever block of code, for loop code is following, or whatever block of code follows if we have curly braces, as we will see later. So the data clause applies to this part of code. So now the data transfer is going to happen once before we enter the outermost for loop, and the data transfer that is going to happen from the device to the host at the end of the execution is going to happen at the end of the outermost loop as well. Of course, I need to go here and comment this out because we don't need this anymore. And I'm going to do the same thing for the second loop structure that we have here. And I'm going to comment this out. So I'm going to compile again. Oops. Sorry. This one. And I'm going to run the same thing. Oh, keep in mind that the last parameter is now not doing anything. It was used for multi-threading. I just kept the parameter to show that I'm using the exact same code. Now we are using offloading to the device, actually. So now this is run, and we can see what the time is for the two for loop structures, the two offloaded sections that we have, denoted with K1 and K2. It is quite big, and especially if you recall how much it took us for the OpenMP CPU code. So why is this happening? First of all, in order to see what is happening with respect to the data transfers, I'm going to use one environment variable that, when it's set, is going to allow us to get some information regarding how time is split across data transfers and execution of the offloaded section itself. So I'm going to use this one here, lib OMP target profile equals true, and I'm going to ask to get the time in milliseconds. So now I'm going to run the same thing again, and you are going to see that we are going to get information about the data transfers and the execution time of the computation itself. All right, so you can see that we get some basic profiling data here. So the data read takes 400 milliseconds, the data write takes 2000 milliseconds, and you can see how much time the offloaded section computation takes. Now I'll go back to the code and show you how we can make this better. And I want to just prove the point that it is very important to have in mind our algorithm, and also keep in mind what I said about the importance of data transfers. So you can see that we have two offloaded sections. One is like the first for loop structure that we have on the top, and one on the bottom. And in between, we actually do not have any computation on the data on the host. So what we are doing here with this Pragma OMP target data mapping is redundant as well. We can actually combine, merge these data transfers and do it only once at the beginning. So I'm going to comment this out. And as I mentioned earlier, I'm going to use I'm going to use a block of code here. So the PragmaOMP data is going to be with respect to the whole, to both the offloaded sections. All right, so I'm going to compile this again, and I'm going to run it. And what we expect to see here now is that the data read and data write times are going to be about half of what they were before, because we are doing it once. And this is what we see here. So, we are going to use this code as the base. So we will consider like the data transfer part done for the purposes of this tutorial. And we are going to use the code as we have it now, and we are going to now talk about how we can optimize the computation time. So to do that, I am going to use some profiling tool, which is called CLI Probe. In order to use this, I am going to source the appropriate paths first, and now I have it on my path. Okay. So what this tool does, it is going to give us some information with respect to what is happening at the lower level, which is the OpenCL layer, because that's how the offloaded code runs on the device at the lowest level. So I'm going to get some information, and I'm going to see how this affects performance and how we can make changes in our code to get better performance. So I am going to run the code that we had before. 16,384, 10.1. So we are going to run it and see what we get from that.
So there's a kind of overhead with the profiler?
I'm sorry?
Is there a kind of overhead?
There's not much
due
no.
to the profiler?
No, there's not much overhead in this kind of profiling tool. It's like low overhead. So what you can see from this profiling information is, first of all, the formatting is not very good because of the screen, but you can get like the time, the number of times each of the offloaded sections is called, and you can get the average time for every invocation, minimum time and maximum time. Anyway, but what I want to focus on here is the GWS and LWS parts. For those of you who have experience with OpenCL, LWS is the local work size, which corresponds to what would be a work group in OpenCL, or a thread block in CUDA, for those of you who have experience with NVIDIA. And global work size is the full iteration space in terms of work items. Now, why I mention this? Because by dividing the global work size with the local work size, you can get the number of work groups that you have. And a work group is, on a higher level, it is a scheduling unit. So here, you can see that we have only one work group at the lower level, and this is very inefficient. This is inefficient because on this integrated GPU, for example, we have 24 execution units, and we can schedule one work group to every execution unit at any given time if there are no dependencies. So in this case, we are actually underutilizing our resources. So what I'm going to do now is I'm going to go to the code and show how we can get better performance by making the appropriate changes. So I'm going to go to the OpenMP directive that is responsible for the offloading, and I am going to use the teams clause. So what this clause, OpenMP offload clause, says is that we want to create multiple teams, not just one like we did before. And I'm going to do the same thing for the other kernel. Teams. Okay, I am going to compile this, and I am going to run it. I'm not going to run it with this big input size because it's going to take forever. But in order to prove my point, I'm going to use a smaller size. What I want you to see from this is that now, dividing the global work size by local work size, we get 24, which actually is the number of execution units in our GPU. So we are now utilizing concurrently all our execution units by using this version of the code. But you notice that I did not run the code with the original parameter because it would be too slow. You would ask, why would that be too slow if this is supposed to be better utilizing the GPU? The reason is in the semantics of the PragmaMP target teams. When we use it by itself, it creates multiple teams. But what every team does is every team has one master thread, and this master thread executes what follows. So every team executes the same code that follows. So we have like redundancy in the execution again. Of course, that would be dumb to do, but I'm doing it like to incrementally show you how we build the best version. So what we are going to do is we are going to supplement this line with a distribute clause, which is going to take the following for loop. It is going to divide it into multiple chunks, and it is going to assign each of these chunks to one team of threads. Like in the interest of time, I'm going to not compile it and run it. We are going to get better performance than we did before, and actually our original parameters execution, our running with the original parameters, the 16K array is going to run, but again, it's going to be slow. So what we want to do is we are going to use parallel for. Parallel for is going to utilize all the threads within a team rather than only one master thread. So now we are making the best use of our resources. So I'm going to do the same for this one.
You missed the distribute.
Oh, did I? Good debugging. All right. Here. Oops, no, we want to run with the biggest one. All right, let's see. So it's supposed to run faster. I hope it does. Yeah, it does run faster now. So you can see now that we went from, the previous one would be around 6,000. We went like to 2,000 milliseconds here. And you can see again that we have a local work size 256 and 6144. Again, I mean, we are never happy, are we? No, we are not. So we are going one last time before we wrap this up and introduce one more last OpenMP clause, which is going to be the thread limit. So you notice that the local work size was 256. We can actually select ourselves what we want the size to be. We don't have to let the compiler or runtime select what it is going to be. So I'm going to introduce this last clause, thread limit, and I'm using for, and I will explain a little bit. Thread limit for. All right. Human compilers, did I do any mistake? I will see. OK, I did. All right, so let's run it one last time and see what the effect of this change is. All right, so you can see that now the local work size is 4. The global work size has been adjusted, but you can notice that still 96 divided by 4 gives us like 24, so we still have 24 works here. And you can see that the execution time went from about 2,000 to 713 and 650 respectively. So we will, and of course, in order to have the best performance, as with the CPU case, it's the same with the GPU. You need like to keep in mind what your underlying architecture is. So you have to know, like I mentioned, specify the number of work groups or the number of threads per work group, etc., etc. All right, so that was pretty much it. So yeah, I'd just like to recap. We did a quick introduction to the OpenMP Offload capabilities. We discussed the algorithm that we used for our example. We saw how we can get portable code with OpenMP from the CPU to the GPU. We discussed issues regarding the data transfers and how important they are for offload programming. And last, we discussed issues regarding the computation offload and how we can get optimum performance. Thank you.